Hello everybody, this is Mr. Koker and this is Module 11 and it's going to be on nuclear radiation. I would like everybody to take the Twizzler I gave you and take it out of its package, and we're going to pretend that your Twizzler has a half-life of 5 minutes, and so I've set an alarm, and at the end of 5 minutes it's going to go off, and at that time I'll tell you what to do. So we'll wait for the alarm, but hold on to your Twizzler, don't eat it yet. We'll wait and see what to do in 5 minutes. Before we get started, I'd like to look at a couple of things we did early on in the semester and just review them, see if you remember a little bit about, first of all, balancing equations. Very important in chemistry to learn how to balance equations. Here we have H2 plus O2 yields H2O. Can you balance that equation? Why would we care about that? This is supposed to be nuclear. So it's important to remember that even in nuclear reactions we need to balance the equations, but the balancing is going to look a little bit different than it does for balancing chemical equations, but we'll take a look at how that works. Secondly, I'd like to see if you remember our symbol notation that we used with element symbols and letter A, which stands for mass number, and Z that stands for atomic number. So if I had an atom with 12 protons, 12 electrons, and 12 neutrons, how would you write that symbol representation, including the element symbol and the A and the Z? And what would it look like if I had an element with 12 protons, 12 electrons, and 15 neutrons? What would an atom like that look like? So I think you probably do remember how to do this. So why don't you pause the video and just do those problems, and when you're done you can turn back on the video and I'll show you the answers. So just go ahead and pause the video now. Okay, hope you're back. Let's take a look at the answers. First of all, the balancing equations. Did you come up with 2H2 plus O2 yields 2H2O? That's a balanced chemical equation. And now for the symbol representations. Did you get Mg with a little 12 in the lower left and a 24 in the upper left? That would be magnesium. Anything with 12 protons is a magnesium atom. The 12 is the protons, it's also the atomic number Z, so it goes in the bottom left. 24 would be the mass number, which is the protons plus the neutrons. So that's why it's in the upper left-hand corner, and it's the A in the AZ element symbol notation. Now, an isotope of magnesium that with 15 neutrons would be 2712 Mg. So it looks very similar, except the 24 is now a 27. Instead of 12 plus 12 equals 24, we now have 12 plus 15 equals 27. So this would be an isotope of magnesium 24 and magnesium 27. They're isotopes. Now earlier we saw balancing chemical equations using the numbers and the subscripts, but now we're going to be balancing, in this module, nuclear equations, and to balance those we're going to use this kind of notation with the A and the Z values. So we are looking now at Module 11, nuclear radiation. That is the radiation symbol for nuclear radiation. So we've been talking about isotopes. Just to remind you, isotopes are atoms with the same number of protons, which means they are the same element, but different numbers of neutrons, so they have different mass numbers. Same Z, different A. The protons and neutrons, of course, are located in the nucleus of the atom. One way to write their symbol would be to write proton as P plus, for P proton, plus for charge. Neutron N0, N for neutron, 0 for charge. Now protons and neutrons have very similar masses. They're both about 1 atomic mass unit, and so they have mass numbers of 1, but their charges are different. The proton is a +1 charge. The neutron has neutral or no charge. Now all of the protons and all the neutrons are going to be found in the... Oh, I hear the alarm going off. So that's our alarm, which means you should go ahead and eat half of your Twizzler. Just eat half of what you have. Don't eat the other half yet until the alarm goes off again. All the positive charge and most of the mass of the atom is in a very small area. You remember what it's called? I thought you did. It's the nucleus. Many isotopes have unstable nuclei. In other words, their nucleus is not stable, and they will spontaneously, without any outside intervention, they will spontaneously emit energy or radiation. So they give off radiation from the nucleus, and they do that in order to become more stable nuclei, or in other words, to lower the energy of the nucleus. So something that spontaneously emits radiation is said to be radioactive. So if an isotope is radioactive, it's an isotope that will spontaneously emit radiation. Isotopes that emit radiation or that are radioactive are also called radioisotopes, radioactive isotopes, or radioisotopes. Radioisotopes can occur naturally, or we have the technology in high-tech labs to actually make radioactive isotopes or radioisotopes. So many of the elements beyond uranium were made in the lab, and they are radioactive. They are radioisotopes. Radioisotopes in our daily life. Maybe you know someone that has some dinner plates that look like this. This is actually a type of Fiesta ware, and Fiesta ware uses a certain kind of glaze that actually is radioactive. And so if you knew someone that has plates that look like this, you might test and see if they are radioactive, and you might wonder how you would test. Actually, you would test using a Geiger counter. A Geiger counter is a small handheld device that you can put up to something, and it will make audible clicks, and the needle will swing on its scale there, and it will show you how much radiation that particular object is giving off. It can detect beta, gamma, and also X-rays. It detects this because of the way those radioactive particles ionize the air. So they actually knock electrons off the air molecules, and that ionization can be detected by this radioactive detector called a Geiger counter. It will actually emit audible clicks. It'll make a little click 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 sound from its loudspeaker, and if you hear the clicks closer together, a higher concentration of radioactivity will mean more clicks, and so when it starts to click faster, it means you're getting more dangerous radiation. It will also register it on a compressed scale analog meter using a needle. The needle will swing to a particular value that you can read on the meter. So what kind of types of radiation are there? There are the ones that are based on the first three letters of the Greek alphabet, alpha, beta, and gamma. And there are also some other types of particles that can be radiation as well, positron, neutron, or maybe a proton. So let's look at some information on each one of these. Alpha particles. An alpha particle is actually 2 protons and 2 neutrons, so in a way it's a nucleus of a helium atom. But it's not helium until it gains 2 electrons and becomes a helium atom. It's a helium nucleus. It's actually emitted by the nucleus of a larger atom. So a larger atom may give off 2 protons and 2 neutrons, which is an alpha particle, and that can be dangerous, damaging radiation. It has a mass number of 4. Its charge is +2 because of the 2 protons. It's generally going to be low speed but high mass. It might be analogous to like a bulldozer. It's not moving real fast, but it's really heavy. It has low penetrating power. You could actually block alpha particles using a piece of notebook paper. It doesn't pass through the skin. So alpha particles are really only dangerous if an alpha radioactive isotope that gives off alpha particles gets inside your body. It can be dangerous to internal organs if you take something internally. So maybe you breathe it in or eat something with the radioactive isotopes. Alpha particles are actually used as part of the way in which smoke is detected in a smoke detector. Oh, I hear the alarm. That tells us that we should now eat 1/2 of whatever is left of our Twizzler. So eat another half of whatever is left. Don't eat the second half. Simply take that half and bite it in half, leaving you with about 1/4 of the original Twizzler. Let's move on. Beta particles. Beta particles have a mass number of 0 and a charge of -1. So they are actually identical to an electron. It's just that they are emitted from the nucleus of the atom. It's actually emitted when a proton converts to a neutron. These are medium speed and have medium penetration. You should use a heavy lab coat and gloves when handling something with a beta emitter. It's actually something that's going to be useful for treating things like malignant tumors. It has a certain penetrating ability, and it can actually kill tumor cells, and so you could use beta particles on malignant tumors to treat them. A positron is actually a positively charged beta particle. So this would actually be identical to an electron, same mass, except instead of negative charge, it's positive charge. You may not have known that there are positively charged electrons. They are actually a form of antimatter. They are the antimatter version of an electron. They're actually called positrons. If a positron collides with an electron, they will create pure energy, according to the equation E = mc². The matter will convert to energy. And so it will actually form a gamma ray if the positron is colliding with an electron. So this could be used actually to scan the body. It's called positron emission tomography, PET, and it's used in some kinds of cancer detection. Now a gamma ray, which is actually a piece of high energy radiation, would have no mass and no charge, but would be just a piece of radiation, a photon, a quantum of energy. It's only energy, it's not mass. It's very penetrating. It can get through lead. If the lead is not thick enough, it'll go through lead. It could be used for diagnostic purposes deep inside the body. It could also be used to irradiate food to kill any kind of mold or germs that may be on food. It could be used for that purpose because it has a lot of energy and it kills cells. So it could be used for food irradiation. Gamma radiation is actually part of the electromagnetic spectrum, which spans all the way from very high gamma rays to less intense X-rays, which are still fairly energetic, to ultraviolet rays, which can also, all of these on the left, gamma rays, X-rays, and ultraviolet can cause cancer. And then slightly less energy, longer wavelength light would be visible light, red, orange, yellow, green, blue, indigo, and violet. Slightly longer wavelength and lower energy would be infrared or heat. Microwaves have even less energy and longer wavelength, and then really long waves would be used for communications like cell phones and radios and television. Anything that communicates through the air would use something with long wavelengths, something maybe close to a kilometer of wavelength. Okay, getting back to the types of radiation, a neutron would be medium in speed. It would have a mass number of 1 and a charge of 0. It's about 1 atomic mass unit. Neutrons emitted from a radioactive source can be stopped by concrete. And then there is the proton, which is a mass number of 1 and a charge of +1. This is actually a nucleus of a hydrogen atom. So a hydrogen atom nucleus would be a proton. Protons can be used for cancer treatment. You would use a cyclotron to accelerate the proton, and depending on how fast you got the proton moving before you bombarded the cancer with it, it would penetrate the body to a depth determined by its speed, and so the doctor would calculate how much energy to put in the proton to determine how deep it should go. There's our alarm. I would like you to take the remainder of your Twizzler and now eat half of what's left of your Twizzler. Leave the rest of it for later. Mass of a proton is about 1 AMU. Let's look at radioactive decay. Radioactive decay is the process of an unstable nucleus spontaneously breaking down, emitting radiation, and changing to a different element or a different nucleus. It's also called radioactive decay. A radioactive nucleus will make a new nucleus and give off radiation. So this is actually how the equation will look. You'll have your radioactive nucleus on the left, the new nucleus it forms on the right, plus its radiation as a second product. This would be an example of a nuclear equation. Let's say you had uranium-238. Uranium is element number 92. So on the left side of the arrow we have the symbol notation for uranium-238. Uranium-238 is an alpha emitter. It will give off alpha particles. Remember, alpha particles are a helium nucleus. 2 protons, 2 neutrons. Atomic number 2, mass number 4. So on the right side we see 4,2He. Now what else would be formed? What is the new nucleus that would be formed? The new nucleus would be thorium-234 with an atomic number 90 and a mass number 234. Now how is this similar to an ordinary chemical equation? Well, obviously the atoms don't match left and right, so that's not the same. It's not even the same number of atoms. You got 1 atom on the left and 2 things on the right. What is true about this is that mass is conserved. The mass number is the same on both sides, and so the mass on the left and the mass on the right are the same. 238 yields 234 plus 4. Also, you may note that the atomic number is the same on both sides. 92 equals 90 plus 2. And so that's part of balancing these radioactive decay equations, is recognizing that the top numbers on the left should add up to the top numbers on the right, and the bottom numbers on the left should add up to the bottom numbers on the right. With that in mind, let's see if you can come up with the answers for these blanks. Iodine-131, which is element number 53, gives off a beta particle, 0, -1. See if you can come up with what the element symbol would be and the mass number and atomic number for that. And when you've done that, go ahead and do number 2 and number 3 and number 4. The M in number 4 simply means that technetium-99 is metastable. It means that it's kind of temporarily stable, but it's not going to last. It's not going to be stable forever. So that's just a little letter designation to mean metastable. Okay, if you need to stop the video and do these problems, go ahead, and we'll start it up here in a second. Okay, let's see if you're completed. First of all, the iodine-131-53 gives off a beta particle. You can either use E or the beta symbol. And it makes xenon-131. So iodine can turn into xenon. The second equation was carbon-11, giving off a positron, 0 plus 1, and turning into boron, boron-11. Notice 11 equals 11 plus 0, and 6 equals 5 plus 1. In the third one, we have radon giving off an alpha particle and forming polonium, polonium-218, PO. You will need a periodic table when you're working these, because you have to be able to look up the element symbols. And finally, the metastable technetium becomes a more stable version of technetium-99 and gives off a gamma particle, 00 gamma. It would be useful to know just how much radiation there is in something. And so there are various ways to measure radiation, and some of these terms that we're going to learn are old terms, meaning they were terms that were used in the early days of studying radioactivity, and then some are newer terms. First of all, if we take a sample that's radioactive, we could detect how active. There's our signal that tells us to eat 1/2 of whatever is left of your Twizzler. It's getting kind of short, isn't it? Getting kind of small amount left, but just eat half of it. Don't eat the whole thing. Back to radiation measurement. Activity is something you could measure for a given sample. You could say just how active is this sample. You could measure the activity in Curies, which would tell you how many disintegrations are happening per second. A Curie is actually named after Pierre Curie. Marie Curie called it after her late husband Pierre. And it stands for the amount of radiation given off by a gram of radium. Radium is a very radioactive element. And so if you're comparing something and you say that it has 2 Curies, what you're saying is it's giving off the amount of radiation 2 grams of radium would give off every second. Now, Curie is actually a very high amount of activity. And so the becquerel was introduced as a new way of measuring activity. And it's a little more sensitive. It's not as large of an amount. It's a smaller unit of activity, and it's called the becquerel. It's a new one. And it actually says that every disintegration per second is a becquerel. And so if your sample is disintegrating and giving off 5 particles per second, then that's 5 becquerels. So that would be the activity of a sample. You might be interested in how much radiation has been absorbed by something. Not how much something gives off, but how much is being absorbed by something. Maybe absorbed by you if you're being exposed to radiation, or being absorbed by some food that's being irradiated. Absorbed, an old way of measuring that was called a rad. They actually said so many rads of radiation. Rad stands for radiation absorbed dose, and it's based on the amount of radiation absorbed by a gram of material, maybe a gram of body tissue. The rad, though, was a very large amount of radiation, and so a more sensitive, smaller amount of radiation is called the gray. And the gray is actually 100 rads. It's a new way of doing it. The gray is actually a smaller number, and so if you have 100 rads, that's only 1 gray. One reason for this is that a smaller number sometimes doesn't sound quite as dangerous, and so maybe the scientists are trying to tone down the radiation fears, and by changing the number from 100 rads, they could say, no, they've only been exposed to 1 gray. Well, it's the same amount, it's just a smaller number. Thirdly, another way of looking at radiation is to look at the biological effects. Different kinds of radiation may have more or less damage on the human body. Just an aside, that picture on the right side is actually the first X-ray ever taken. It was taken of Wilhelm Röntgen's wife's hand. You can even see the wedding ring on her hand there. That was actually the first X-ray ever taken there. Of course, when she got that X-ray, she was exposed to radiation, and the radiation can have biological effects. It can damage cells, and it can increase the risk of cancer. The one way of measuring radiation is the REM. REM actually stood for radiation equivalent man, or the radiation equivalent in humans. It's a common way to measure the biological effect. So the amount of REMs might be different depending on whether you're exposed to alpha, beta, gamma, X-rays, or different kinds of radiation. So the rim has actually been mathematically adjusted to help determine the amount of biological damage from radiation. The sievert is a different unit. Actually, a sievert is 100 rems. So similar to what we did with rads. We took rads and we made 100 rads equal a gray. 100 rems equals a sievert. And so a sievert is a unit that just doesn't sound quite as terrible. If you get 300 rems, you've only gotten 3 sieverts. It's actually the same amount of radiation. 3 sieverts would equal 300 rems, or 1 sievert is 100 rems. So, 3 different ways to look at radiation. The activity of a sample, the absorbed dose of a sample, or then the biological effects. Well, there's our alarm again. If you've got any Twizzler left, eat half of it. Now, where can exposure to radiation come from? Well, there are naturally occurring radioisotopes in our surroundings. We are not totally protected from radiation because there is radioactivity all around us all the time, naturally occurring radiation. There's radiation that we get from being close to the ground, from our air. For example, radon in the air is radioactive. Water, food can have radiation in it, radioactive isotopes in it. Cosmic rays from space, wood, concrete, brick. So the stuff our houses are made of are giving off radiation. In fact, concrete and brick can give off more than if you lived in a wood house. You're actually getting more radiation because the brick is made from clay from the ground, which has radioactive isotopes in it. Maybe you get a dose in millirems from a chest x-ray or a dental x-ray. You ever wonder why they put that lead vest on you when they give you a dental x-ray? Why does the dental technician go in the other room to turn on the x-ray? Why don't they stay and stand there next to you? Well, x-rays are radiation, and they give you a dose of radiation. Hip x-rays, lumbar, spine x-rays, mammograms, upper GI. Let's say they have you drink the stuff and the barium stuff and then give you an upper GI x-ray to see how your intestines are working and your stomach is working. That's actually a very high dose of radiation that way. Yes, you get radiation from sitting in front of the television. Or air travel. Air travel. Why does air travel give us radiation? Well, actually because it puts you closer to space, where cosmic rays will get into your body. And then radon. Radon is a very dangerous, depending on where you live and what your house is built on top of. This can vary widely. You may be getting as much as 200 millirems annually from radon gas. You can actually test for radon gas in your home and see if your house has a dangerously high level of radon. If you would want to do it on Cobra, there's actually an Explore Your World Module 9 that will allow you to calculate your millirems for your annual dose to see if you in particular are being exposed to a lot of radiation. So, naturally occurring isotopes, medical and dental procedures, air travel, radon, smoking cigarettes. Actually, radon is the second leading cause of lung cancer, only second to smoking cigarettes. Radiation can make you sick. For example, the people who lived near Chernobyl, which was a nuclear plant in Russia that exploded, I believe back in the 80s, or I believe it was the 1980s. Chernobyl was a nuclear power plant in Russia that had an accident and exploded and blew a bunch of radiation all over the community. And some of the people who were near there and got exposed to that radiation got sick from that radiation. There were actually about 200,000 people involved in trying to clean up after that nuclear power plant blew up. And each one of them received an average of about 100 millisieverts. So is that a lot? Well, let's say you were working for a month and you got 100 millisieverts from cleaning up after Chernobyl. That's actually going to be a lot more than the 2.5 millisieverts per year that a normal person gets. And so they got quite a bit more than a normal person would get. Of course, any exposure is going to increase your risk of cancer. So it's not just that it makes you sick, it can also give you cancer. There's two things. Radiation can actually make you physically sick, or it can actually increase your risk of cancer. With medium doses, let's say you don't get cancer from a medium dose, you might, but let's say that you roll the dice and you don't get cancer from medium dose, but you may be nauseous, you may have vomiting, fatigue, your white blood cell count may go down. This often happens to people who are treated with radiation for cancer, to kill cancer. They can get sick and have fatigue and reduction of their white blood cell count. High doses can actually cause diarrhea and cause your hair to fall out. Once again, we see this in people with cancer and trying to treat the cancer. There's the alarm. If there's any of your Twizzler left, eat half of it. Okay. Will radiation kill you? Well, it might kill you, but it might kill someone else at a different level than what it kills you. Not everybody has the same tolerance and same strength and ability to resist dying from radiation poisoning. So when we look at things that are poisonous to us, like radiation, we talk about it in terms of an LD50, lethal dose at which 50% of the subjects exposed to that much dosage will die. So this averages it out over a population of, say, 100 people. So out of 100 people, looking at table 9.7 on the right there, 50 rems, I'm sorry, that would be 500 rems. 500 rems, if I took 100 people and exposed them all, each one to 500 rems, that would be enough dose that half of them would die. So that would be the lethal dose for half of them. Dogs are slightly more sensitive to radiation than humans, so radiation kills the dog more than it kills the human. But rats have more tolerance for radiation, a bacterium has a very high tolerance, and insects have the highest tolerance. So if we kill ourselves all in a nuclear war, the cockroaches will survive. So different organisms have different lethal doses for radiation. You do not need to memorize these numbers, by the way. Okay, the whole thing with the Twizzlers is actually to illustrate half-life. Half-life of a radioisotope is the amount of time needed for half of the sample to decay. So let's say that we had some iodine-131. Remember, iodine-131 decays and forms xenon-131. If you started with a 20-gram sample, after one half-life, and half-life can vary from isotope to isotope, but for one half-life, after one half-life, 10 grams of your original iodine would be now turned into xenon, and the other 10 grams would still be iodine. After two half-lives, you'd be down to 5 grams. The 10 would cut in half to 5, and the xenon would increase to 15. After 3 half-lives, you'd be down to 2.5 grams of iodine-131 and 17.5 grams of xenon-131. So you see, every half-life, you lose half of whatever you had at the beginning of that half-life. 20 goes to 10, 10 goes to 5, 5 goes to 2.5. So you actually never go to 0, you just keep cutting in half, just like you've been doing with the Twizzler. See? Told you that Twizzler had something to do with nuclear radiation. Your height of your Twizzler has been decreasing by half every 5 minutes. We have a 5-minute half-life. So I believe we're up to about 6 half-lives by now. So you should see a very small amount of your original Twizzler. If we were to graph it, it might look something like this. Let's try some half-life problems. Let's say we had some technetium-99 metastable, which has a half-life of 6 hours. If we started with 80 milligrams of it, and we ended up with only 10 milligrams left, how many half-lives would have passed? And since a half-life is 6 hours, how many hours would have passed? Now, the second problem would be a problem based on gallium-68. Gallium-68 has a half-life of 68 minutes. Every 68 minutes, the amount of gallium-68 has cut in half. So if I started with 50 milligrams, and I administered this gallium-68 to a patient at 8 a.m., how many milligrams would still be in the patient? In other words, how many would not have decayed yet at 1:40 p.m.? So you can do the math and figure out how many half-lives there are, how many 68 minutes occur between 8 a.m. and 1:40 p.m. And our third problem for practice on half-life problems is, let's say that we consider a radioisotope to be gone after 10 half-lives. Well, you saw how little of your Twizzler was left after 6 half-lives, right? So generally, you can say anything radioactive has been completely depleted after 10 half-lives. So let's say we have some phosphorus-32. It's radioactive. It has a half-life of 4.3 days. How many days until we would consider the phosphorus-32 sample to be completely gone? I'll pause here, let you stop the video, do these problems, and then we'll check our work. Okay, ready to check the work. Let's see how you've solved these. The technetium-99m problem, how would you solve that? Well, if we go from 80 to 10, how many half-lives is that? Well, let's just work backwards from 80. 80 milligrams becomes 40 milligrams after 1 half-life. 40 becomes 20 after 2 half-lives, and 20 becomes 10 after 3 half-lives. So to go from 80 to 40 to 40 to 20 and 20 to 10 would take 3 half-lives. And if every half-life is 6 hours, that would be 3 half-lives times 6 hours over 1 half-life equals 18 hours. Let's take the gallium-68 problem. How many half-lives would there be from 8 a.m. to 1:40 p.m.? Well, 8 a.m. to 9:08 would be the first half-life. 9:08 to 10:16 would be the second half-life. 11 to 11:24 would be the third half-life. To 12:32 would be the fourth half-life. And 12:32 plus 68 minutes would be 1:40 p.m. So 1, 2, 3, 4, 5 half-lives. So if you have a 50 milligram sample, and it cut in half 5 times, or in other words, 50 times 0.5 times 0.5 times 0.5 times 0.5 times 0.5, or 50 times 0.5 to the 5th power, that would end up with 1.5625, or 3 sig figs, 1.56 milligrams left. So the gallium-68 that you originally gave this patient at 50 milligrams would be depleted all the way down to 1.56 milligrams by 1:40 p.m. that day. Or another way we could do it was we could say from 8 a.m. to 1:40 p.m. is 5 hours and 40 minutes, or 340 minutes. 340 minutes times 1 half-life over 68 minutes equals 5 half-lives. So that would get the same way as counting it up the way we did up above. And the third problem, the phosphorus-32 problem. If a half-life is 4.3 days and it takes 10 half-lives for it to be gone, then it would take 43 days for the phosphorus-32 to be completely gone. Now, of course, remember, it's not completely gone, it's just been cut in half 10 times, and that's pretty much all gone. What would be some medical applications of radiation? Remember, we're going on that field trip on Thursday to Presence Health Center to take a look at their medical imaging department and their nuclear radiation medical nuclear medicine department and their X-ray department, just to look at medical applications of radiation. These can be diagnostic. That would be low levels of radiation used to look inside the body and image organs. So X-rays and things like that, maybe CAT scans and X-rays. But medical applications can also be therapeutic. So diagnostic, detecting a problem like detecting a broken bone or detecting cancer, like a mammogram to detect cancer. Therapeutic would be high levels of radiation used to actually intentionally kill tissue. Of course, you would point the radiation as much as possible at the damaged or diseased tissues or the cancerous tissues. So using radiation to kill cells that you don't want in your body. If you're going to do medical applications of radiation and you're going to use radioisotopes, you're probably going to choose ones with short half-lives. If you're going to inject your patient, you don't want them walking out the hospital with a lot of radioactivity still going off inside their bodies. So with short half-lives, then you're going to be able to give them the radioisotopes, detect the problem, and then move on. Okay, let's take a look at half-life and medical radioisotopes. These are 6 radioisotopes. Which ones would be useful for medical purposes? The carbon-14 dating would not be useful. It's got a half-life of 5,730 years. It's used for carbon dating for detecting how old a very old object is, but it's not very useful for medical purposes. Cobalt-60 might be useful. In fact, it was used for years to treat cancer. The doctor that used it, of course, would have to keep in mind that his cobalt-60 sample was getting half as effective every 10.5 months. Now, usually, if you're going to bombard cancer with radiation, you'll probably use something like a linear accelerator, which is kind of a more artificial way to give radiation to the cancer. Iodine-131 is actually kind of interesting. If you put iodine in the body, it will go to the thyroid. The thyroid is kind of a butterfly-shaped gland that gives off hormones in your, it's actually kind of deep in your neck. If somebody has Graves' disease, which actually causes hyperthyroidism, in other words, the thyroid is overactive and giving off too much hormones, which can make you have some bad symptoms, you might actually want to slow down the thyroid by giving somebody some radioactive iodine. Radioactive iodine will collect in the thyroid and actually kill some of the cells of the thyroid and slow the thyroid down, so it slows down the emission of the hormones. Or possibly you have thyroid cancer. It's also useful on prostate cancer. This will actually concentrate the radiation at the thyroid because you're trying to kill the thyroid cancer. So iodine-131 could be useful for that. Technetium-99 metastable has about a 6-hour half-life, and so if anybody uses this in the lab, they're going to need to replenish it fairly often, maybe even on a daily or every other day. You need to get a new sample in because every 6 hours it's going to go down by a half. So in 24 hours it's been cut in half 4 times. It's usually used for imaging. Many body parts will actually show up on an image if you inject technetium-99 into the body. So the skeleton, heart, brain, liver, lung, spleen, kidney, and also the thyroid. Uranium-238 has a half-life of 4.5 billion years. Well, maybe not useful for medical purposes, but is used in nuclear energy. So, nuclear energy, what's that about? Nuclear energy is when we take advantage of the energy given off during a nuclear reaction. There are actually 2 kinds of nuclear reaction that can give off and release energy. One is called fission, and that's where you split atoms like uranium-235 into 2 smaller isotopes, like krypton-91 and barium-142. This is accomplished by hitting the nucleus with a neutron. Now, when a nucleus of uranium-235 is hit with a neutron, besides the 2 isotopes, 3 more neutrons are given off. And if those split isotopes, then you see that you can quickly get a reaction that goes out of control. You can have a chain reaction where the atoms split, give off neutrons, those split more atoms which give off more neutrons, and you can end up with a chain reaction. So a nuclear bomb. Or if you carefully control it so that it doesn't expand and get bigger and bigger and more atoms, just kind of gradually breaks down atoms. You can do that by absorbing some of those neutrons that are being given off so it doesn't expand. You can have a controlled chain reaction, and that can be used to produce nuclear energy, like Clinton Power Plant. Fusion is actually the energy source of the sun. The sun uses nuclear fusion, and it's the combination of hydrogen isotopes to make helium. And the difference in mass between the left and the right side becomes energy. Remember, E equals mc squared, so mass can actually be turned into energy. This is what a nuclear power plant, kind of simplistic diagram here, but it's kind of how a nuclear power plant might work. You would take water from some water source, a river or a lake, for example, Clinton Lake, and that would be your cooling water. And then you would have some fuel rods, which would be undergoing some fission in the fuel rods. You would have your control rods, which would absorb the neutrons. So the operator, I don't believe it is Homer Simpson at Clinton Power Plant. I believe he works in Springfield. So control rods would actually be moved up and down in the reactor in case the reaction tried to get too fast, or if you needed to speed it up, you could pull the control rods out and speed it up. Now the reaction occurring in the fission reaction occurring gives off heat, which can be used to heat hot water or maybe some molten sodium, and then the heat from that molten sodium or hot water can be used to generate steam, and steam can power an electric turbine and make electricity. Now after the steam has turned the turbine, you need to cool it back down so it can be run through the cycle again. And how do you do that? Use cold water from the lake. So the cold water from the lake comes in, it cools down the steam, turns it back to liquid, and then the water that leaves is going to be hot. If you've ever been around the Clinton power plant, the water actually is quite warm near the power plant. And that's from the cold water that was used to cool the steam down. So notice the water that goes back into the Clinton Lake is not radioactive. It's fairly far away from the actual radioactive fuel. It's a different part of the cycle. But all it is warmer when it goes back into Clinton power plant. So the fish you catch in Clinton power plant are not radioactive. Let's take a look at the good and the bad news for fission and fusion. Fission is easy to do. Doesn't take a whole lot of technology. We've learned how to do it in the last 80 years or so. It involves radioactive isotopes, so it does mean you have to have quite a bit of safety involved. If anything leaks into the environment, it would pollute the environment with radiation. Also, the isotopes needed for fission are fairly limited, so the fuel is difficult to get your hands on. It's only certain amounts of fuel available in the ground. And the worst part is it produces a lot of radioactive waste. And the big question is, what do we do with the remaining leftover radioactive waste? Let's take a look at what it looks like for fusion. The bad news for fusion is you got to get it up to about 100 million degrees Celsius to get fusion to work. And you know, there's just not many containers, or any containers, that can handle that kind of temperature. So what do you put your fusion reaction in? Probably some kind of very powerful magnetic field, which you could generate with an electromagnet. But the amount of electricity it takes to make the magnetic field with an electromagnet is greater than the amount of electricity you generate with the fusion reaction. So fusion is just not cost effective. Of course, we could just take advantage of the fusion reaction occurring on the sun and use solar panels and just collect the radiation given off by the sunlight. But it would be a cheap, safe fuel because it would use hydrogen and it would make helium. So we're not talking high radiation levels. So that about wraps us up for the nuclear radiation. Remember, you want to prepare well for the Presence Hospital visit and study up on balancing nuclear equations and how to do half-life problems. So those are the math for this particular unit. Also, you might want to study up on the different kinds of ways of measuring radiation. Rads, REMS, grays, sieverts, things like that. So thanks for your attention, and see you in class. Oh yeah, fusion has limited radioactive wastes.